Simple series and parallel circuits are found in all kinds of electronic devices. However, many electric motor circuits and control circuits are made up of complex networks called series parallel circuits.
There are two basic types of series parallel circuits, one in which a resistance is connected in series with a parallel combination, the other in which one or more branches of a parallel circuit consist of resistances in series.
Now, let's analyze a simple series parallel circuit to see how total resistance is affected.
Connect three wire-wound resistors having the resistance values of 10 ohms with one resistor in series with a parallel combination of the other two. This forms a series parallel circuit, and the total resistance is found by breaking the circuit into parts consisting of simple series and parallel circuits. The two 10-ohm resistors in parallel are equal to an equivalent resistance of 5 ohms, as determined by the product sum method. This equivalent resistance is now in series with R1. Therefore, RT equals R1 plus R equivalent equals 15 ohms. Connect an ohm meter across this network. Reading the top scale of the ohm meter, the resistance reading is 15 ohms. Reconnect the three resistors with two resistors connected in series and the third resistor connected in parallel across the series combination. The total resistance is found by adding the two resistors in the series branch to obtain the equivalent value of 20 ohms. This value is in parallel with the third resistor, and by using the product over the sum method, results in a value of 6.67 ohms. RT equals 20 times 10 over 20 plus 10 equals 6.67. The value is checked with the ohm meter, and it is 6.9 ohms, which is within the acceptable tolerance of the resistors.
We've just applied the basic rules of finding the total resistance in complex series parallel circuits. If any of the parallel combinations have branches consisting of two or more resistors in series, find the total value of these resistors by adding them. Using the formula for parallel resistance, find the total resistance of the parallel parts of the circuit. Combine this total parallel resistance with any resistance that's in series with it.
To demonstrate the effect a series parallel circuit has on current flow, connect a 10 ohm resistor in series with a parallel combination of two 10 ohm resistors. Connect 3 ammeters in the circuit as shown in the schematic, and connect the circuit to a 10-volt supply. With the wiring completed, close the circuit switch and notice the current values as indicated on the ammeters. The total current on ammeter A1 is 0.4 amperes. The total current readings on ammeters A2 and A3 for the two resistors in parallel are 0.2 amperes each.
The total current for a series parallel circuit depends upon the total resistance of the circuit and the voltage source.
Current flow in the circuit will divide to flow through all parallel paths and come together again to flow through the series part of the circuit. The total current is the same at each end of a series parallel circuit. Rewire the circuit, making the 10 ohm resistor R1 and the 10 ohm resistor R2 a series connected branch in parallel with the other 10 ohm resistor R3. Close the circuit switch and observe the readings on the 3 ammeters. The total current reads 1.5 amperes, with 1 ampere flowing through the 10 ohm resistor R3 and 0.5 amperes flowing through the series connected branch of R1 and R2. As in parallel circuits, the current through any branch resistance is inversely proportional to the amounts of resistance. The greater current flows through the least resistance. To analyze the division of voltage across a series parallel circuit, connect the circuit as shown. Each resistor is 10 ohms. Close the circuit switch. Measure the voltage across R1, 10 volts. Voltage measured across R2 is 3.33 volts. R3 has a voltage drop of 3.33 volts. And R4 also has a voltage drop of 3.33 volts.
Notice that although the currents divide through the different paths, the sum of the voltage drops of any one path always equal the source voltage.
Therefore, the voltage across R1 is equal to the applied voltage, or 10 volts, as is the sum of the voltages across R2, R3, and R4.